children.
Okay, well, thank you all for coming. As I was saying to Patricia, she had a little competition today, but obviously
I'm better than Ray Cross.
the great people know where to come. So we're going to hear today from Patricia Cleary from the Chemistry Department about a study of air quality over Lake Michigan and ozone, and I'll let her tell you all about it.
Great. So I'm going to talk to you about my study of air quality over Lake Michigan and tell you the final summary of it. That we measure observations of ozone that are higher than are at the shoreline, which is kind of to be expected, but they're much lower than what's predicted. So everybody thinks there's high ozone out over the lake, and it is a little bit higher over the lake, but it's really not as pronounced as the models predict. And it took a lot of time and effort, multiple years worth of data sets, and a lot of years of analysis to come up with this conclusion. So I'm going to go over some of the what went into my conclusion, a little bit what goes into the chemistry of ozone formation in the troposphere, the measurements that were taken at the shoreline using differential optical absorption spectrometry, observations on a ferry, and then what we did to compare those to forecast models. And we even expanded and compared it to all EPA sites in the general area to show the difference in bias over the lake versus anywhere else where ozone's being measured. So I like this slide from the EPA that ozone is good up high, bad nearby. So when you hear about ozone, what do you think first? What comes to mind? The ozone hole, absolutely. So this is a big deal. We know that ozone is necessary for protecting our living bodies from harmful UV radiation. And what goes into ozone formation higher up in the atmosphere isn't what happens in the lower atmosphere. But let me give you an orientation of the atmosphere. So, oops, woo, nope, pointer, come back. So this is a diagram of the temperature profile of the atmosphere, where the lowest part of the atmosphere is the troposphere. And this red line is the temperature profile. So as you go up, it gets colder, and everybody who's been on top of a mountain or seen a mountain that's covered in snow has seen that it's colder as you go up. As a chemist, we could describe this phenomenon as an adiabatic expansion of a gas. So we can follow the thermodynamics of the temperature profile. It's somewhat similar, except we've got water in there. It complicates things a little bit. But this is mostly an adiabatic expansion of a gas. Once we get to the stratosphere, the next layer of the atmosphere, the temperature starts to go up. So why is the temperature increasing in the stratosphere? Does anybody know?
I'm not going to answer.
Huh? You know. What? Yeah.
Chemistry.
Chemistry, photochemistry. So the ozone layer is absorbing UV radiation that gets converted into kinetic energy. So the oxygen molecules, O2, gets photolyzed, making oxygen atoms. They can react again with O2 to make O3. That's what's going on up here. There's a lot of energy that's being absorbed from the sun and being converted into thermal energy into new molecules. So this is chemistry driving this higher temperature. And what's interesting about the stratosphere is that it's hotter than the troposphere. It's stable, it's stratified. So we've got hotter air on top of colder air, and that changes the dynamics of the stratosphere and the troposphere. Those effects can be even seen on a smaller scale in the troposphere, but the stratosphere has a different circulation pattern than the troposphere because of how stable it is. There's not a lot of mass that's transferred across the tropopause, and it's like this cap on the troposphere here. So the tropopause is just that layer that we call the boundary between the two. So we will see more inversions like this on a smaller scale in the troposphere that also confines air masses. So on the really large scale, the stratosphere has lots of ozone. It's formed by a unique chemistry up there that's that we can't have going on in the troposphere. And we also have limited mixing between the two. Yes? It's down by a factor of 100 to 1,000. So, I mean, I'm right up to 10 kilometers, it's not down by much. But then by the time you're up here, I think you're, huh? Oh, here we go. So, here we go. So 10 millibars, yeah, down to 1 millibar at the top of the stratosphere. Yeah. Okay. So let's think about the troposphere now. So now I'm telling you that ozone is actually bad to be nearby, and it's regulated. So according to the Clean Air Act, we still have that thing. There is an ozone standard. And right now it's an 8-hour standard, and that standard just got changed actually October 1st to 70 parts per billion. And these are the counties, this is based on the earlier standard of 75 parts per billion mixing ratio of ozone. And so California is not meeting air quality standards. It historically rarely has met these standards. The Chicago area is not meeting them. You could see a lot in the Northeast.
Are there any counties in New Jersey that are meeting?
No. But so you'll see like these large coastal areas where you know there's a lot of population. You'll see some areas where there's not a lot of population. There's some other drivers going on there.
What's happening when you cross from Connecticut into Massachusetts?
Connecticut, what? Oh, this is just the urban corridor. All of this. This is that like, it's something like a third of the US population is in the Northeast. It's a quarter. So you just have a dense population of people, urban areas, lots of emissions, bad air quality. Okay. But all along the Northeast corridor, there's lots of it. And so you'll see some counties like here. Okay, one of the counties that sticks out in Wisconsin is Sheboygan. It's not known as a hotbed of urban activity. And it's not a place that has a lot of manufacturing or, it's not like the Northeast corridor or California.
You know, Sigma Aldrich is in Sheboygan.
Yeah, I don't think this is from just from Sigma Aldrich. What's going on here is that there are regional effects from urban pollution in Chicago that goes out over the lake. The lake helps sort of vent out urban emissions and distribute them into a wider area. And you'll see some of that also, like Cleveland isn't that big of an urban area, but where you have bad air quality it extends almost as big as the Chicago area, but Cleveland isn't that large of a city, but it's next to the lake. So there's an enhancement near the lakes. And this has been seen more over the years. There was a lot more pollution where maybe 10 years ago where there were a lot of counties surrounding Lake Michigan that were in non-attainment. Now the only two in Wisconsin are Kenosha and Sheboygan, and not in like the Milwaukee area because you can have local emissions that actually make it a little bit better, which is like a titration event that I'll describe a little bit. So, and if you want to think about the standard of 70 parts per billion, okay, I'm not going to talk much about these mixing ratios, but if we want to get a picture in our mind of what 70 parts per billion means, there are 7 billion people on the planet. And, nitrogen, if the people were molecules in the atmosphere, nitrogen would be 5.5 billion, 1.3 billion would be oxygen, that would be China, okay, the population of China would be oxygen, and then about 490 people would be ozone. So that's such a very, very small number, and yet that has health impacts. Okay. So we can look at the predictions are that the ozone is high over the lakes. This is an air quality forecast model. And the experiment that I conducted really was, can we start to probe what's going on over the lake? So the ferry transect is here from Milwaukee to Muskegon, and then I had a shoreline measurement in Kenosha. I've also put in this picture triangles that represent power plants, just so you can get some idea of largish power plants, not just any power plant, but I forgot what my cutoff was, like 7 gig of something. I've forgotten.
Coal burners or all?
Coal burning, yeah, or natural gas. I would use either. But they're kind of giving you some indication that there's power plants and activity like that around the lake. So in order to make ozone in the troposphere, we need 3 specific requirements. You need to have a stable environment, so I'll call that a temperature inversion. So I showed you, a really large scale temperature inversion that you get between the troposphere and the stratosphere. We can also have really small inversions where you have hot air sitting above cold air on a really small scale. So, and what I mean by small might be that this height is 300 meters instead of 10 kilometers. Like I lived in a house for a while that had hot air vents on the ceiling, and you can feel that, like if you're sitting down in the room and then you stand up and you can feel the hot air sitting near the ceiling. Well, this is exactly the same thing that happens, and this is what confines the chemistry. Like in the atmosphere, we don't have beakers to mix stuff around. We have to have stable air masses that don't mix widely into the rest of the atmosphere so that the chemistry can happen. It makes the beaker, if you want to think about it that way as a wet chemist. We need sunlight to initiate a lot of the chemistry that I'm going to talk about today to make ozone. And then we need precursors. So there are 2 types of precursors. Nitrogen oxides, this comes from inefficient combustion, so your Volkswagens emit a lot of NOx. And volatile, it's like 10 to 40 times as much, they said. Like, oops, yeah, we kind of lied. We made it not do that. And then volatile organic compounds, so this is anything that you can kind of smell that's organic. Benzene, so off of gasoline, your paint as it's drying and you smell that, that's a volatile organic. Fingernail polish, when it first starts to smell, there's some solvents in there that are being emitted. Yeah?
For fingernail polish, they don't have oxygen.
Volatile organic. It just has to be organic. So some of them can be oxygenated, some of them don't have to be. So whatever can volatilize, we will just call it a VOC.
Never thought of roses as being dangerous.
Yes. Well, actually, biogenic compounds like oak trees emit isoprene, which has like a gas kinetic rate in the atmosphere of oxidation. So actually, a lot of areas that have a lot of deciduous trees have a lot of volatile organics that we can't do anything about because the trees are emitting isoprene to tell each other something. I don't know if we know what, but so we have to think about ozone production in terms of a regulatory issue and how we understand what's going on with the chemistry and how we can control the ozone precursors such that we don't build up too much ozone in the atmosphere. So I have a mechanism that looks like it's this sort of engineering diagram. I'm gonna go reaction by reaction in this to maybe make it a little bit more less cluttered, let's say. So we've got our volatile organics here, and we've got our nitrogen oxides here. We need a little sunlight in order to make the hydroxyl radical. This OH is like the cleaner of the atmosphere, so it initiates a lot of reactions that begin to remove volatile organics from the atmosphere. So this OH molecule can react with a VOC, which readily can react with O2. Remember, this is China versus the 7 billion people, so it's always around to make a peroxy radical. Once we make this, and this is my organic chemistry, that R contains carbons and hydrogens and maybe other stuff too. But we've made a peroxy radical with that organic compound. And that reacts with the NO portion of NOx which converts it to NO2. So it's just the oxygen being taken away from this RO2 and placed onto the nitrogen oxide to make NO2. NO2 can photolize in the atmosphere, making an oxygen atom which attaches to my readily available oxygen, O2, to make O3. So it needs to go by this mechanism, a VOC making a proxy radical, the proxy radical reacting with NO to make NO2 to make this conversion. There are other things, there are other reactions in the atmosphere that make this inefficient. There are other ways to make NO2 that may photolize to make ozone, but they're like a closed loop, and they won't lead to the buildup of ozone. So it has to go through this by mechanism to build up. And I'm giving you an ideal situation where nothing terminates this reaction. We might add more oxygen to some other oxidation product to make a secondary peroxy radical, the hydroxy peroxy radical. So in general, for every VOC that's oxidized by OH, we should generate 2 peroxy radicals and 2 molecules of ozone. And this chemistry is what's going on in the atmosphere, this confined atmosphere. We like to think about this cycle as something that's occurring as this plume leaves an urban area. There are ways in which it's slow or it's terminated inside an urban area. If you have too much NOx, it can gum up this cycle. If you have too little VOCs, it's not efficient. And so all of the chemical models have to use hundreds of VOCs and figure out where this plume is and running this chemistry in some sort of confined space without really good boundaries. So this is the chemistry that exists inside the models, but we need to actually understand a lot about the individual volatile organics, where these nitrogen oxides are, how long they're lived, and all that to get a big picture of how ozone is building up in the atmosphere. And measuring ozone and then testing our models is one way to get an idea of whether or not we understand how efficient this cycle is. And that's what my experiments are trying to get at. So this is a map of Kenosha, where the first experiment was conducted, which is a DOAS instrument over the harbor here. This is a picture of my spectrometer. This is the light source. This is the receiver. So you can see the light source has this like kind of shining light right over there. The path length is 600 meters. So some people have an idea of like a spectrometer, and they think of like something that you put a little cuvette in the lab with a 1 centimeter path length. This one requires a 600 meter path length. And this is all about the fact that these are very, very small concentrations of gases, and we need a lot of opportunities to send light through those for them to absorb the light in order to measure them. So 600 meter path length is required. This is a picture from the emitter looking out to the receiver, which is right here. So from mounted to the top of 2 buildings, we have a spectrometer. Yes?
What are you using for a light source?
A xenon lamp.
Oh, cool. So it's broadband.
Broadband. And what's nice about this is that because it's broadband, I can look through several different spectra, and I can look at several different molecules. I'm not going to, so here's like emitter, receiver, and then there's a monochromator inside my instrument, so I can scan through many wavelengths. And then at different wavelengths, there are different compounds that are absorbing. So I can look at, in this specific experiment, I looked at ozone, SO2, NO2, and formaldehyde. And so they have different areas of the spectrum that we can see them. Yes?
Differentiating between that and the background radiation by pulsing it, or what are you doing?
No, it's a differential measurement, so you're going on and off of a line. That's all. So that's why these spectra don't look like nice, big, broad UV absorption spectra. They look like funny little squiggles, and that's because it's a differential measurement on and off of a small line. So I'm going to cut to the chase and tell you about what I saw at the shoreline. So this would be one season's worth of data in 2009, where these are wind profile measurements. Here's ozone, and I see more ozone coming from offshore. So starting with the north to the south and coming from the east, those air masses tended to have a higher ozone mixing ratio than coming from the west. Similarly with SO2, whereas NO2 seemed to be coming more from the southwest. And formaldehyde, where I could measure it, there was a lot of measurements that were below the detection limit of formaldehyde, were also coming from the southwest. What's difficult about telling you a story about this picture is that it's not just about like, okay, well, everything offshore is just all ozone. There's a lot of ozone coming out from over there, and then all of the NO2 is coming from the southwest. There's a complication with the lifetime of some of these compounds. So NO2 and formaldehyde have a shorter lifetime. So both of these are photolized in the daytime. So you're going to see them build up and be higher at night. And my winds generally came from the west at night because of the circulation patterns near the lake. And SO2 and ozone can stay around in the atmosphere for up to a week. And so what's coming from over the lake could just be more aged. Okay, so there are some complexities there that don't stick out. Yes?
All this measurement 24 hours,
Yep.
7 days.
Yep. That was about 3 months, 3 or 4 months worth of data to show you those 4 little graphs. Yes. And so here's what's going on at the shoreline. There's this lake breeze circulation, which relates to the differential heating of a landmass and water. So the heat capacity of water is higher than of rock, which means in the daytime, when the sun is shining on rock, it actually heats up much faster because the heat capacity is lower. So just the temperature goes up. As that happens, then you get hotter air, it rises, so long as it's not capped off, we call that low pressure. And this can still move offshore in whatever sort of dominant airflow is going on. But over the lake, it's colder, so the lake isn't heating up as quickly, so we would consider this high pressure, and so it's backfilling in whatever low pressure is on shore. And this boundary is called a lake breeze front. And it can be observed, like sailors know that this exists. They try to like sail along it if it's offshore. And it moves throughout the day. But typically in the middle of a hot summer day, you will have winds coming off the lake. And so in southeastern Wisconsin, they will be going to the west. Whereas we always think of air masses kind of going east, in the eastward direction. Another way that you can observe the lake breeze is a front where if there's air that's rising that has water in it, it'll reach a certain point where you will form clouds. So rising air can form clouds, and so you can see that there's rising air forming clouds all the way around here, but not anything that's encapsulated by this lake inversion. And I found this nice diagram of like, why is it always rainy in the UP, right? So they have the lake on both sides. They will get fronts and clouds on 2 sides from Lake Superior and Lake Michigan because of that warm air rising over land. And Florida, sure. So the next experiment that I want to talk about is looking at the ozone over Lake Michigan. So the ferry makes 4 trips a day most of the year, and then 6 trips a day for a shorter amount of time during the year. So only from between July and August, there's 2 extra trips at night. And there was a small ozone sensor, well, I'll call it small, it was like this big, placed in an interior room on the Lake Express, and the inlets were up on top. So this is the inlet. I don't know, showing a box in a mechanical room isn't very exciting. This is a little more exciting. And the ozone was also measured in this way. So just as the ferry is running, it's measuring ozone. And here's a demonstration of, okay, a year's worth of data. The black dots are the data that was obtained and it looked good. So there's some points that are taken out because either the ferry wasn't running or the instrument wasn't running or whatever. This is from 2009. And then on top of that, I've got the model, and I'm going to tell you a little bit more about the agreement with the model. But the model data was collected concurrently with the measurements. And you can see the black points tend to lay below the red points. So we're measuring ozone over the lake.
Impressive, right?
Huh?
So the broader trend, how
Yeah.
the model is sort of modeling the general parts of this, right?
Oh, yeah.
Missing a little bit on the quantities.
Yes, yes. Your R squared is pretty good. So we get good correlation. It's just that the slope is wrong.
And that's grabbing like meteorological inputs primarily?
Yes.
And then also some of the precursor measurements?
Yes. Well, there are emissions inventories, so there's an estimation of the emissions. And most of these large trends tend to be like how you turn up the chemistry or how you confine the air masses. And so that seems to be captured pretty well because like on a cold day, the ozone's just not going to be high. Yeah. It's a TECO instrument, absorption, ozone absorption.
Multi-pass cell kind of thing?
Yeah, it's actually a single pass and there are two different cells and they switch between the two of them so that you can get a 0 to cancel out any absorption of water so that we don't have a...
Calibrated to ozone.
Yeah, they're calibrated against standards because of course ozone is ephemeral, if you want to think of it that way. So there's like the monitoring networks have like the gold standard of certain instruments that measure really well, and then everybody has to compare their instruments to those. So I've been able to send my instrument back to NOAA to get it closer to the primary measurements. Some interesting things that you can see in the relationship between what we see at the harbor. So if we look at this panel right here, I've got my DOAS measurements in red and the ferry measurements in blue, and they basically track each other pretty well, not totally well, but in this example right here, we got the dotted lines. It's a really good example of when the wind shifts at the shoreline. So this is the wind measurements, and you can see this like cut out, like a really stark wind change. That's when the shoreline measurements of ozone really drop down and they stay high over the lake. So it's one way to show that, yeah, ozone can stay elevated over the lake, whereas at the shoreline, meteorology and local emissions can really change what the chemistry that you see. So one thing that I did was I compared the measurements over the ferry and as a function of different variables. So let's say this is my difference. So I took the ferry measurements and I subtracted the ozone measurements at the same time. The ozone measurements at Kenosha as a function of the distance from Milwaukee, as a function of temperature, as a function of wind direction. And this top black panel is like all data all the time. It's just a little bit higher, but there's very little trend in distance from Milwaukee or temperature. If there was a trend here, then we could say something about the chemistry. It's indicating something about like we don't understand or that there's different chemistry that's happening farther away because there's some timing that has to happen. It's almost like a kinetics experiment where you can like, sort of send some contaminants in and kind of watch them as they go. We're not really seeing that in these observations of temperature or distance. Wind direction has some variability, and clearly like if the wind is blowing this way at Kenosha, and the ferry's over here, you're getting not the same measurement because you're sampling different air masses. And the only time that really they're most significantly different, I separated them out by different times of day. Then this is morning, green is morning, red is afternoon, and blue is evening to late at night. This is the only time where those diverge, this is pointing more towards a meteorological difference. It's a confinement issue than it is chemistry. And there's a year's worth of data. There's a lot of parts that I'm trying to compare. Yeah?
Is that why in the highlight section there in temperature, is it because the air masses are different temperatures too? So the fact that they're coming from different directions causes a bias?
So it's the temperature as measured at the shoreline. So that, yeah, the temperature could still be very different over the lake at that time. But again, you don't see that, whoop. I'm not seeing that necessarily just in all data, right? It's really only at night. And it's not even the hottest temperatures. I got higher temperatures for the other time periods. So we had all this data. The next thing that I want to do is just compare this to what we're modeling. What are we thinking? How are the regulatory agencies actually modeling what's going on over there? And so the way that the forecast model works is that you've got the weather model first. So you got, their historic data sets and all that to develop the weather models. Then they have a weather forecast to say, okay, tomorrow it's going to be 60 degrees and sunny or whatever. That forecast then gets plugged in to an air quality model. Here's where we use biogenic and anthropogenic emissions. So we need emissions inventories. We have to have some sort of guess at what cars are going to be driving, what their emissions are going to be, what kind of industrial activity, what kind of plants are emitting, what kind of compounds. And that all comes together for an air quality forecast. And I always get to this point where, I think like, now how do I justify my existence, right? Like, why is it important to do this model comparison? And clearly, the Volkswagen example is really key in saying, okay, all of our forecast models are based on emissions inventories that usually happen at the tailpipe during the emissions testing. It's not, well, we've measured every car on the road and we know what's going on. They're just scaled up estimates. So if there's some trickery going on when those tests are being done, then we can't model the chemistry right. And so there's one example. This came about because this guy, I can't say his name, no way. West Virginia University, he was like, well, I'm going to study what's actually coming out of the tailpipe. That's what I'm going to do. I'm going to send these on the road. I'm going to measure this. And someone might go, well, boring. Like, why do you want to, stick a little sensor in the back of a moving vehicle? But they clearly came up with some trends that were alarming based on the available data. I also know some people at the University of York in England who did something very similar, well, something different, and came up with some similar results where they were looking at diesel-related hydrocarbons emissions, and they just looked in London and they're like, whoa, there are a lot more diesel emissions than what we have in our emissions inventories. So they did just the whole atmosphere measurements and said, something's going on here, like we're getting all these large hydrocarbons that are actually contributing to aerosol. And there's this big question mark, like we're not getting our emissions inventories right. And now, of course, we're seeing more diesel car makers kind of being questioned about this. So the way that this data is represented is a little weird, so I'll talk you through this. What this is like a spatial temporal representation of the model. So this would be a ferry transect. So the x-axis is longitude, and then the y-axis is time. So at 6 p.m. or 6 a.m., this purple dot signifies the model grid cell ozone prediction for that space. And so this is actually running through time all the grid cells that the ferry would be at as it moves across. So you can kind of see like 1 day's worth of data where ozone is high a little bit in the afternoon, and the model is predicting that it's high on the sort of eastern side of the lake. So this is, about 15 hours in central daylight time, 16, 4 o'clock in the afternoon, that's when ozone is predicted to be high. And then I've got 2 different forecasts. One is a 1 to 24 hour forecast and one's 25 to 48 hours. So they initialize the models every 6 hours, but then they run them for 48. So it's just like how you capture them, and we can look at how well a 48-hour forecast works. And essentially, it's modeling something a lot higher. This just represents how many data points we have of every ferry transect at that one grid cell that we do the comparison for. And this is the actual observation. So the color represents the real ozone observations, which still are high. The highest ozone observation is in this late afternoon, but it's not nearly as high as what's forecast. Another way that we can evaluate this is with bias. So we just take our modeled ozone and we subtract our measured ozone. And then here, the 16 parts per billion is that difference. And so the 1 to 24 hour forecast is over predicting by 16 parts per billion. And we're much more over predicting to the longer forecast.
Jackie,
Yeah.
the model ozone is from your the weather forecast plus the emission from the.
Yes. That is the air quality forecast model output. And then we can also look at that with respect to like all ozone measurements. So all of these dots here are where there's a station that's measuring ozone. And the ferry measurements are here. So you can see that, 14 to 17 is yellow to red. So these are higher over predictions than some of these that are blue, which are still over predicting by maybe by 6 or 7 or 8 parts per billion. So what we're seeing is that it's over predicted, and anywhere on land except for maybe in inner cities, it's over predicting by quite a lot. The reasons why there's an over prediction here, like in Chicago, might have more to do with local chemistry of titration than it would here. So in Chicago, you might have really fresh sources of NOx, which decreases the ozone, which would make your prediction over-predicted if you didn't know that NOx was going to happen. Over the lake, there's something a little bit different going on. And what we think is going on is that pollution is kind of going up and over the inversion instead of into it. That is my guess. And so the way I want to test this is to start to evaluate the distributions across that frontal boundary using UAVs, unmanned aerial vehicles. So we can try to look at whether or not there's a chemical and meteorological boundary that sort of exists up and over. Oops. And that's the next step. But with that, I'd like to thank all of my co-authors and my student workers and the funding and water utility for letting me mount a big instrument to their building. And I'd like to thank you for your attention. Yeah.
What's the power source on that boat?
The power source on the boat is a diesel engine.
Diesel.
I'm pretty sure.
Could the output from that?
You can totally see it because you get a titration. You see zero ozone if you're catching the plume. So we see it because the sensor, the inlet tube is mounted to the top and towards the front of the boat, and the exhaust is out the back. But anytime that thing turns around or it's in port, it just shoots down to zero. You can see it immediately.
But all those measurements you have shown is 60 parts per billion, right? And you're talking about that right now it's like a 70 parts per billion.
Yes.
It's still quite low then.
Yes. Yeah, well, and then it's an 8-hour average of 70 parts per billion is the new limit. So then they say you have to like not do that multiple times a season. Maybe you do it once and you'll still be considered in attainment, but if you have like 4 or more days, so it'll have to be like so many days that it crosses that threshold. Yes?
That's my question. So with the standard being reduced to 70 parts per billion, these aren't all, I mean, a lot of these cities or these regional ozone sources are they're model results, right? And whether or not they're attaining is often model results. So the fact that the models are over-predicting ozone, isn't that kind of a compelling?
It's, their non-attainment status is based on the measurements in that county. And so Kenosha County stays in non-attainment and it has a monitor that's right along the lakeside. So people complain because it's actually in an area that's really probably not like the air quality in the greater Kenosha County. It's like right along the lake, which we know is going to be a little bit higher because there's no titration going on there. But that puts it in non-attainment, the actual measurements. But how you deal with it being in non-attainment has to do with modeling. So you have to say, well, we want to reduce these emissions here, and then it'll be fixed. But if they're not modeling it right in those communities, then it won't work.
So what are the health effects of ozone?
So it's if you have sensitive mucous membranes, it makes anybody with respiratory illness worse. So you increase people who have heart and lung problems going to the emergency room. That will happen more when ozone is high. More asthma problems, and then it actually impacts ecosystems as well. So it'll influence cell walls and stuff like that. But for the most part, I mean, when I moved to California, I didn't really think too much about bad air quality. And then I had a day because I had asthma, but it wasn't really bad. It was under control. And then they're like, people with asthma shouldn't go outside. And I was like, whatever, it's fine. And I was like walking. It felt like I was on top of a mountain. Like I just, it's not like I had an asthma attack, but I just couldn't breathe. Like there's no oxygen in the air. That's what it felt to me. You know, I was just like drained of all energy. It was really weird. Yeah.
So speaking of that California data, I mean, there's a lot of non-attainment in California. Recently, there's been some suggestion that some of that is ozone
Asia.
coming from across the Pacific.
Yeah.
That seems like a long transit to me. What's
Yeah.
your thoughts on that?
So I think it's all about whether or not there's a baseline. Like if the baseline ozone is 20 versus 30 parts per billion over in the marine environment. They can see plumes, you know, at Trinidad Head and stuff like that of like particles.
Yeah.
But ozone, you know, it's not going to be lived for much longer than a week. And that's a week's worth of time for it to move over there. But are you changing the chemistry in the marine boundary layer that is like 15 to 20 parts per billion? So you're adding, you have background that's coming in and then you're adding all of the pollution on top of that. That's the question. Like they're really concerned about this in England because it's a little bit closer to cross the Atlantic from North America, and they're trying to measure what that background is. And I think they do feel like there's maybe a 5 parts per billion in the marine environment that's altered just because of North America. I think it's a harder sell for across the Pacific because it's a long way. But it's a small effect, but it's like if you're starting here versus here and then you put all that pollution on top of it, where's it going to go?
So when are you going to fly the UAV?
When they won't crash. We've been developing a system, and they've been doing some test flights. We did one test flight with my ozone sensor, and it crashed under 2 minutes. And my ozone sensor is like $5,000, and I was like, ah! And I'm like running at it. And so when we can get reliable flights in, then we'll fly it. So there's been testing. We've been working on it, but we'll wait till the flights are okay. All right, if there are no further questions, thank you so much for coming.
Thank you.